Okay, so the recording is started. Then, so in today's lecture, we are going to continue our discussion on the multivariate normal, which we started before the midterm. So I hope to conclude some discussion on the multivariate normal, and then we are going to draw the connection from the multivariate normal to the distribution, specifically the chi-square, the t, and the f distribution that we introduced before the first midterm. Okay, so just for recap, before the midterm, we talk about multivariate normal, or maybe let me also put it down. So multivariate normal distribution. So whenever we talk about multivariate things, it's referring to like a random vector. So for example, here y, it's a n by 1 vector. And then for each of the elements, you can use like an index or any index that you want to in the subscript as the index for each of the elements. So for example, y is a column vector. So you will have a column vector of y1 to yn. So that is n by 1 matrix vector. Yeah. And then for this multivariate normal, we will write y is following a normal distribution. And here is up to your preference. You can write a dimension in the subscript here if you want, just to make sure you know that this is an n by 1 vector that you're talking about or working with. And then you will also have two particular parameters. The first parameter is called the mean mu. Here, the mu is also a column vector. So here, let's write down, and then you can also use the index mu1, mu2, all the way to mu n for this column vector. And it also has the dimension of n by 1. And then we also have a covariance matrix, and we denote it as a capital sigma. So if you use latex, if you do lowercase, this is the lowercase sigma, the Greek letter, and then this is the capital Greek letter for sigma. Okay, and then here for this sigma matrix, this is a n by n matrix. That means you have n by n multiplied by n elements to fill in to this n by n matrix. So here for the 1, 1 entry, you have sigma 1 square. So here we can use the lowercase sigma to denote each of the elements in this matrix. And then for the 1, 2 entry, you have the sigma 1, and then you have a 2. So you have two index to indicate the location for this elements. So this is your 1, 2 entry. So you have two index. And then you have all the way to 1n, and similarly 2, 1, and then you have n1. And then for the diagonal matrix elements, you have the sigma 1 square, sigma 2 square, and then all the way to sigma n square. So these n by n multiplied by n or n square elements will consist of your sigma matrix. And then as you already noticed, or the sigma matrix or the covariance matrix should always be symmetric. So that means a sigma transpose is equal to sigma. And just to elaborate a little bit on this transpose operation, this T, capital T, on the superscript here, the transpose is referring to, so for a vector, so for example, when you have a column vector, let me just use like a bar to denote this is a n by 1 vector. And let's denote this as a y. And then for y transpose, you essentially just rotate it and then make it a row vector. So now you have the 1 by n. So if y is a column vector of n by 1, then a y transpose is just a row vector with a dimension 1 by n. And then for the matrix form, so let's say we have a matrix A. Let's say for just for explanation, let's design this as a 3x2 matrix. So you have A11 and then A12 and then A21 and then A22, and then here you have A31 and then A32. So let's say this is a matrix A. And then when we talk about the transpose of a matrix, this will becomes a 2x3 matrix. And then for the elements are A11, A21, and then A31 from here, from your original matrix A. And then you will have A12, A22, and then A32. And then you can generalize for an arbitrary, say, m by n matrix. So this is just a brief elaboration on this transpose operation. So I hope this will just to give you some introduction for all of these operations when we move to the matrix vector notations. Okay, and then now let's write down the density function, which is also the probability density function of y. So you can write f of y for the normal case. So now they are essentially the same, except they are just some notational difference because we are moving to the matrix vector multiplication thing. Okay, so again, you have this normalizing constant, 2 pi raised to the power of negative n over 2. And then again, n is referring to the dimension here, n by 1 column vector. So this is a multivariate with a n dimension vector. So here you have the n over 2 for the 2 pi. So if you think about, you have like a 2 pi for a scalar, and then you have another 2 pi for a scalar. And then when you multiply n copies of them, you have 2 pi raised to the power of n. But don't forget, the scalar version, you have the 1 over 2 pi, which is in the denominator and also a square root. So that's why you have a negative sign and an n over 2. Okay, just in case if that is not very easy to remember. Yeah, so just think about the scalar version. You have the negative 1/2, and then you have n copy of them. So it's negative n over 2. Okay, and then the second component is the determinant of the covariance matrix. And then here, just don't forget raised to the power of negative 1/2. So if you forget about the powers here, you can think about also the scalar version. You have the 1 over 2 pi sigma square, and then under this square root. So that's why you have the determinant, and then also in the denominator, and then you have a 1/2 power. So here you have n copy of them when you multiply n copy of 2 pi. But here, it just raised to the power of negative 1/2. And then you have the same exponential term. So here, we are going to write everything in the matrix vector multiplication. So again, you have the 1/2. Let's see, maybe let me make it here. Okay, and then you have the y. This is your random variable, or if you want, you can use the lowercase, your random variable. So this is a n by 1 vector. And then minus the mu, again, is the n by 1 vector. And then you have a transpose multiplied by the inverse of this sigma matrix. So this is a n by n matrix. When you take the inverse, it's also going to be a n by n matrix. And then you have, again, the y minus mu, and then closing the parenthesis. So for here, you can just think about also the scalar version. You have, for example, like x minus mu over sigma squared, and then you have a negative 1/2. So here we're just mimicking this formulation, but in terms of the matrix vector multiplication. So you have the 1/2 here, and then you have the x minus mu for this y minus mu. So when you take the difference of two column vector, you also ends up with column vector, so n by 1 vector. And then here you have the power of 1/2, negative 1. This is referring to in the denominator. Yes, because well, I don't want to confuse you, but the elements here, for the diagonals, they already have a square. So here you just raise to the power of 1/2. But here you have the square term. Yeah. And then you have, again, the square of them. So that's why you need to write it as a quadratic form. Okay. Just in case if it is difficult to remember this formulation, you can always draw the connection to the univariate case. Okay. And here, let's just also check the dimension. So you have a difference of a n by 1 vector minus another n by 1 vector. So you end up with an n by 1 column vector. But then you have a transpose. So let me put it here. You will have a 1 by n row vector. So similar as a figure, which is something that look like this. Okay. And then for the second part, you have another n by n matrix. When you take the inverse, it still stay the same dimension, n by n. And then here, again, is the column vector, or the difference of two column vector. So you have n by 1. So altogether, when you multiply this quadratic form, you should have a scalar, or 1 by 1. So 1 and 1. So you will have a scalar here inside the exponential term. The determinant is also a scalar, and then the 2 pi raised to the power of that is also scalar. So that will give you the density as a scalar. So although these are matrix vector multiplication, this one should return a scalar or a real value. Yeah. Okay. Once we have that, we can talk about the special case, which is the standard normal. So here we use the letter z. Here z is also a n by 1 column vector. And then for z, we have the n dimension multivariate normal, except that your mean mu is all going to be 0. So here, this 0 is referring to a 0 column. So there are n zeros in this column vector. And then you have this identity covariance matrix. So this is also a n by n matrix. And this n by n matrix is specified as you have only 1 on the diagonal, but for all the other elements, they are going to be 0. And this is the definition for an identity covariance matrix. So the 0 is a column vector of 0, and the identity matrix is just a diagonal with 1, and all the off-diagonal elements are 0. Okay, so for this normal, we can write down our special case for the standard multivariate normal. So here it stays the same. And then for the determinant of an identity matrix, it's going to be 1. So you have a 1, a scalar 1 here. And then for the exponential term, you have the negative 1/2, and then z minus a 0, so you still have a z. And don't forget there's a transpose. And then for the identity matrix, when you take the inverse, it's still going to be identity. And anything multiplied by identity is still going to be itself. So you have the z transpose again, and then the last part is still going to be a z. So this will be your probability density function for a multivariate standard normal distribution. And then just to write down the dimension, so Z is a column vector of n by 1. When you take the transpose, it's 1 by n as a row vector. And then you multiply by another n by 1 column vector, so you end up with 1 by 1 as a scalar. Okay, so this is just a recap for the multivariate normal and the multivariate standard normal. And then we also talk about the joint moment-generating function. So yeah, so all these are just recap. You already have these notes from your previous lecture notes. So let me just write it down again. You have the joint version for the multivariate normal. So again, you use the letter m to denote the name of this function. And here, this x here is going to be a vector. Or if you want to be more specific, you can write like a x1, x2, and then xn, if you want to be more specific. Or you can just write x, and then you can point out that this x is a n by 1 vector. Okay, and again, the moment-generating function is a function of t. So here, t is also a n by 1 column vector. So now everything is in terms of vector and matrix. And then you have the same definition, the expected value for the exponential. But here, you need to write it in terms of a vector multiplied by another vector. So you have the column vector t, then take the transpose, and then multiply by a column vector x. So again, row vector multiplied by column vector, you should get a scalar. And then you have an exponential of a scalar. And then that will also give you another scalar. Okay. And then just to elaborate a little bit on this inner product or this vector multiplication. So essentially, all these, like a vector notation, it's just to make the operation, when you have lots of elements, to make this notation more compact. But what this inner product or this vector multiplication is essentially just the element-wise multiplication, and then you sum them together. So here you just have ti multiplied by xi. When you multiply each of the elements and then you sum them together, you just have this matrix vector multiplication thing. So for example, this t, you have t1 all the way to tn, and then this x, you also have x1 all the way to xn. So for matrix or vector multiplication, it's just the scalar version when you multiply the scalar, and then you sum them together, and then you have your matrix vector operations. So it's very similar to the scalar version. It just makes the operations for lots of elements more compact. So that's the only difference. Okay, any question or comments up to this point? Okay, so another thing is that, and also this is related to your homework. So in one of the homework problem, maybe I just use the example from homework. So you have a joint moment-generating function for x1, x2, and x3. So this is a 3-dimension version. So in this case, that means x is just a x1, x2, x3, like a 3 by 1 vector. And then you also have this t1, t2, and t3. So in the homework problem, the problem was asking for the marginal moment-generating function, which is referring to the moment-generating function for x1 only. So from the joint moment-generating function, And to get the marginal homogeneous function, you just need to set whatever you don't want for those t to 0, and then you will get the marginal homogeneous function. So if you want the marginal for x1, that means, question?
Could you just repeat that?
Yeah. Let me also write it down. So if you want the marginal, for example, in this case, for example, if you want the x1, the homogeneous function for x1, you can start from the homogeneous function for the joint. So x1, x2, and x3, but you can set the x2 equal to 0 and x3 equal to 0. So the idea is that you can set whatever you don't want, and for those corresponding t's, you set them equal to 0. And then when you evaluate that homogeneous function, that will give you the marginal homogeneous function for the variables that you are actually interested in. Yeah. So in this case, if you want the marginal homogeneous function for x1, you just need to set for the joint homogeneous function, and then for t2 and t3 equal to 0. And then when you evaluate, for example, you will have a formulation here. When you plug in t2, t3 equal to 0 in this formulation, and then that result you will get is the marginal homogeneous function for x1. Yeah. And then this will also work for a subset of these variables. So for example, in the question, we also ask you the homogeneous function, let's say x1 and x3. And then you have t1 and t3.
No.
Yeah.
You could just set x2 to 0.
Yes, exactly. So again, start from the joint homogeneous function that include everything. But you set the t's that corresponding to the variables that you don't want to 0. So the t1 is associated with the random variable x1. The t2 is associated with x2, and t3 is associated to x3. So here, you only want the x1 and x3. You don't want the x2. So you just set the associated t2 to 0. And then after you evaluate this result, you will get the homogeneous function for x1 and x3 only, or the random variable that you're interested in. Yeah.
So in a way, you're just trying to find the correlation for T1 and T3 separately?
Oh, so can you say that again?
No, so when you do this type of calculation, you're just trying to find the correlation between T1 and T3 only, separate from the rest?
Not necessarily correlation, but their association. Yes. Yeah. They're yeah.
Or
The
they work together, because I'm not understanding what exactly does this do.
oh, what do you mean by exactly? So
Mm. So you're saying that T1 and T3 are associated. We're finding the association. What does that association imply? Is what I'm a bit confused about.
we don't know yet.
Oh,
Because here I'm just using a homogeneous function in a general sense.
okay.
But if you're really interested in the detailed association, then you need to look into. So, for example, here, let's say x1 and x3. Then you need to evaluate the homogeneous function. So, for example, like expected value for e of t1 multiplied by x1 plus t3 multiplied by x3. So you need to evaluate this expectation. And this expectation is the integral. And then in this case, you have two variables, so it will be a double integral. And then you have t1 x1 plus t3 x3. And then here, you need to multiply by the joint density function for x1 and x3, and then dx1 dx3. And then the association, the thing I think related to your question is that how you can get this one. So, but this one you need to get also from the marginal from x1, x2, and x3, and then dx2, and this will give you the density function for x1 and x3. So I think related to your question, the association for x1 and x3, you would need to integrate over the density function with respect to x2. Then you will know the association between x1 and x3. I think maybe this is more related to your question. Yeah. But here we are just talking about the moment general function. Yeah. The moment general function is just it's just useful to get like a x power of 1 and then x power of k. Yeah. But if you want the association, you need to going back to the density function for your further analysis. Yeah. The moment general function is just to get the x raised to the power of k thing. Yeah. But a very good question. Yeah. Thanks. Yeah. Any other question or comments? Okay. So one thing that so you don't necessarily need to look into the density function specifically is that their independency. So for example, okay, just let me use the example but basically this is the solution. So, so for example, here you already have the marginal moment general function for x1. And then you can also do the same for the, let's say, x3. And then you get t3. And then you can apply the same thing for x1, x2, and x3, and then set t1 equal to 0, set t2 equal to 0, and then set t3. And then after evaluating at this thing here, you will have your moment general function for the marginal x3. One thing that is useful is to check the independency between x1 and x2. So for example, here we have the moment general function for x1 and x3 only. And then we also have the marginal moment general function for x3 and the marginal moment general function for x1 only. And then you can check whether the moment general function for x1, x3 is it equal to the product of x1 only multiplied by x3 only. So if this is equal, then maybe let me use, if they are equal, or this equation holds, then you can say x1 and x3 are independent. So this is something you can check. And then if they are not equal, then x1 and x3 are not independent. Yeah. But beside the independency, if you want to know more information regarding your random variable x1, x3, you should go back to investigate the density function. Yeah. But for the independency, you can use the moment general function to check. Yeah. Okay. So this is just one comment for this joint moment general function. So for random variables that are vectors, so essentially you have a random vector. Okay. Think that is just a brief. Okay, so I remember before the midterm, I also provided 2 more results. So let me just repeat or write it down again. So just to refresh your memory. So for the moment general function for a random vector z that follow a okay, so since I'm just going to reiterate again, so let me write it more complete. So here let z be the n-dimension 0 vector and identity. And then last time we calculate the moment general function, and this is our result from last time. So all these are just vector. And then last time we calculated, and then we get this result. So this is the exponential of 1/2 t transpose t. Okay. And then also we evaluated for a general normal for a mean mu and then the arbitrary covariance matrix sigma. And then the homogeneous function that we get from last time has this form. So if you want the details for these, you can check the lecture notes from I think lecture 6. Okay. And then sigma t. Okay, so these are also just two results that we developed last time. So now let's start something new. So let's say I have a particular transformation, or maybe I can also write as like an example. So let y following a general normal with mean mu and the sigma matrix. So this is a n by 1 and then n by n, and this is a random vector n by 1. So let's say we have a particular transformation. Let's call it a multiplied by y plus c. So basically it's a linear transformation of a random vector y. So you can use any dimension, so just make it more general. Let's say the A is a m by n matrix. So you can multiply in any dimension, so they don't need to be equal. You can use a n by n matrix A, but here I'm just going to make it more general, like a m by n matrix, so they don't need to be equal. And then your y is a n by 1 vector. And then your m is going to, your c is also going to be a column vector, m by 1. For this one, you need to match the dimension to the result from here. Otherwise, this summation is not valid. Okay, so let's say we have this particular transformation. And now this example, or we are interested in the homogeneous function for this new random vector. So this will give you, let's give it a name. Let's call it x, okay. And this x is also going to be m by 1 column vector. But this is a new random vector, and then it's obtained as a linear transformation of a normal random vector. So let's say we are interested in this new random vector, x. And we're interested in this homogeneous function. And what can we develop the homogeneous function from here, or for x? So one thing is that we can apply the same trick for the scalar version, and then we can achieve our homogeneous function for the random variable x, which is the new random variable. So we have the homogeneous function for a multiplied by y plus c, and then a column vector of t. And then we can use our definition again, the expected value for exponential. Okay, let me use exp from now just to make it like a larger here. So you have t transpose, and then multiply by the whole thing here, ay plus c. And then closing the square bracket, closing the parenthesis for expectation. So here, I'm just using the definition for a multivariate homogeneous function, which is this one here. So the t, again, is your column vector t, and the x is your column vector, or the random variables, x. Yeah. Except that the x is now a transformation in terms of ay plus c. Okay. So again, this is still the definition for a homogeneous function. E raised to the power of t multiplied by x. And I'm going to write x as ay plus c. Okay. And then we can expand the exponential term. So you have the expected value for exponential and then T transpose multiply by AY, and then plus another T transpose for C, and then closing the parenthesis for expected value. Okay. So just to check the dimension, so your T here is a m by 1 vector. After you take the transpose, you have a 1 by m. And then in the parenthesis, you will have a m by n and then n by 1. So you will also get a m by 1. So writing it this way, it's a valid operation because you have a 1 by m multiplied by m by 1 vector. And then same thing here. This is a 1 by m, and then C is a m by 1. So again, it's a valid operation. So the things for the matrix vector multiplication is that make sure, or it's a good habit to check the dimension very often. Otherwise, if the dimension is not matching, you cannot perform a particular operation. So the order here always matter. So you have to write the T transpose first, and then you have to put the AY, and then in this order. You cannot arbitrarily change the order. So for example, in the scalar version, you have A multiplied by B is equal to B multiplied by A. But here, AY, if they are matrix and vector, this is not necessarily equal to Y multiplied by A. And then this is not a valid operation. You cannot even perform this multiplication. So the orders for the element, for this terms matters. So that is just one thing. So and also things that it's very easy to make mistakes in homework or in exams. Okay. Okay, next we can further expanding this. So you have the exponential of a sum. You can reduce as the product of two exponential. So you have the exponential of T transpose A multiplied by Y, and then multiplied by another exponential of T transpose C, closing the expectation. And then here, this thing does not involving any random variables, because the T is just the input of the function. The C here is also a constant. So the whole thing together is a constant. And then it does not involving any random variable. So you can move it outside the expectation operation. So that means you have the following equation. You have the E T transpose C multiplied by the expected value for let me still keep it here without changing anything. AY. Okay, so what I did in this line here is that this term here is not a random variable, it's a constant, so I can move it outside the expected value. Okay. Next, I'm going to make some changes in this order in this matrix vector multiplication. But here, you just need to be very careful with the orders here. So to make the change, or in this particular grouping, we are going to write it in this way. So exponential of A transpose multiplied by the column vector T. And then here, I'm going to group these together and then add another transpose here, and then multiply by the random variable Y. Let me use square bracket just to make it. Okay, so the square bracket is for the exponential term, and then this parenthesis here is for the expected value. So so now I have changed the order, but we also need to verify or to double check whether this operation is valid or not. So again, also from just a side note, AB transpose is equal to B transpose A transpose. And then let's say this is m by n, and then let's say n by k. So here the dimension is matching, so this will give you a m by k matrix inside the parenthesis. But when you take the transpose, your result should be m by k. So now we need to double check whether the right hand side will also give you a k by m matrix. So B transpose, so you will have a k by n matrix for the B transpose. And then you need to multiply by A transpose. So A is m by n, and then A transpose is n by m. So again, you will also get a k by m. Okay, so just to put down this result for you, that AB transpose for matrix is going to be B transpose A transpose. And we also just check that their dimension is matching. Okay. Okay, then with this result, let's also check the things in the square parenthesis. So you have A transpose T. So your A, let's say A is, here we define as a m by n. M by n. So you will, after transpose, you will have a n by m. And then your T matrix vector is also a n by 1. So you will have the dimension matching. So you should get a n by 1 column vector. And then you have a T transpose, so that will make it a 1 by n. And then when you multiply by y, this is another n by 1. So you will get another 1 by 1. Okay. Yeah, so here it might look very tedious or trivial, but I'm just elaborating through checking the dimension just to show you these very trivial details that they indeed matching. So yeah, it might look a little bit boring at this moment, but I just want to give you this result by checking again and again for all the details. Yeah. Okay. So what I'm doing is that when I write it in this way, it's essentially the same as what we started with. But now the problem is, why do I want to write it in this way? Any thoughts? That's one reason. There's another important reason why we write it in this way. So another reason is that here we essentially reduce to the moment function for random variable y. So if you think about this as a t, let's say t star, then you have a t star multiplied by y, and then you have another exponential, let's say expected value. So here, this is just your moment function for y with t star. And then for the moment function of y, we have developed this result in the last lecture, and this is the form. And then we can borrow this form to our equation there to ease the computation. Yeah. So just to reiterate it again, why we write it in this way is that we can group A transpose T as your new T, and now it will reduce to the moment function of y. And then we already know the moment function for y. So now we can just borrow this expression into our result here. Okay, so now let's borrow that result here. So you have the same constant term, T transpose C here. And this expected value, or this moment function, let's borrow from here. So you have exponential T star transpose mu. Okay. T star transpose mu, and then plus 1/2 T star transpose sigma T star. So the mu and the sigma here is because your random variable y is following a normal with mean, mu, and the sigma matrix. This is given here. So just to summarize at this stage, so we know that the y is a multivariate normal with mean, mu, and sigma matrix. And then we have a particular transformation that give us a new random variable that we denote as x. And then here we are interested in finding out what is the momentum function for x. And then through this development, we end up with this notation here. And this notation we recognize as the momentum function for the random variable y, which we already know is formulation. And then we borrow that piece of information here that could ease our computation. The only difference is that here we have the T star because we define the T star, or we group the T star as A transpose Y. So also let me write it down. So here the T star is the A transpose T. The T that is originated from here. Okay. And then we can just bring in the T star here to elaborate the result. So the constant part stay the same. You will have a exponential, let's say T star is A transpose T. So A transpose T. And then you have a transpose for this T star. So that's the transpose from here multiplied by mu plus 1/2. And then T star again, you will have A transpose T. And then another transpose from here. And then a sigma matrix. And then A transpose T. And then that will close the exponential term. Okay, now we can just simplify it a little bit by removing the transpose operation. So here, let me also write it as the exponential for T transpose C. And then exponential. So transpose of AB is equal to B transpose A transpose. So you will have T transpose here, and then A transpose transpose. So when you, let's say, transpose into a, let's say a column vector transpose into a row vector, and then you take another transpose again, you just return back to your column vector. So A transpose transpose is just A itself. So then you have this to simplify the notation here, and then 1/2 T transpose A sigma A transpose T. Okay. So just a little simplification on the notational part. And then we can group this term. Because the product of two exponential is just the exponential of sum. So you will have the exponential for T transpose. And I'm going to group these two terms together because they are sharing a copy of T transpose. So you have A mu plus C, and this C is coming from here. And then plus 1/2 T transpose. And then you have the A sigma A transpose multiplied by T. Okay, so now by looking at this expression, does that look to something that we're familiar with? Anything? So actually, if you think about it, or maybe let me add another parenthesis here. So if you look at this form and then comparing with the moment function of a normal random variable, you can see that the form that we derive is also has the same form as this moment function of a multivariate normal. So that means our transformation dx equal to ay plus c. So this thing also follow a normal distribution. Yeah, but right now the question is, what is the mean and the variance here? So based on your readout from this expression, what should be the mean for this random variable x here? So it should be this part. Yes, a mu plus c. So a multiplied by mu, the parameter for y, and then plus c. But what about the covariance matrix here? Which is just this part, which is a transpose, a sigma a transpose. So the transpose is on the last term here. Okay, so that is our distribution for the new random variable x. So again, just to summarize, we have the standard normal, and this is the moment function for the standard normal. So it's also, as you can see, that if you set mu equal to 0 and sigma equal to identity, this form will reduce into this expression. And this is just the moment function for a general normal. And now, in this example, is that we have a linear transformation of your random variable y. We denote that as x. And then here we are evaluating the moment function for this new random variable after the linear transformation. And after the derivation, we end up with this form. And then we can see that this is very similar to the moment function of a normal distribution. And then we can make the conclusion that x also going to follow a normal distribution. And then with this new mean vector and this new covariance matrix. Yeah. So now let me ask you another question. What is the dimension for this, for x? Or I think I already talked about that. So yeah. So if you want, I already write it down here actually. Yeah, because your random variable x is a m by 1 vector. So if you want, you can also write a m at the subscript here, just to make emphasizing that this is a m-dimension multivariate normal distribution. Yeah. So we started with a column vector of n by 1 column vector or random variables. After the linear transformation, we get a new column vector with m dimension, and this m dimension new random vector also follow a normal distribution. It just with this particular new mean and new covariance matrix. So that is what this example is showing. So if you want, you can call it as a result, or a theorem is that a linear transformation of a multivariate normal random variable also going to be a multivariate normal distribution or multivariate random variables. Okay, so that is the first thing here. So or if you want, can call it a result 1. Maybe, or so in addition to an example, or you can also call this a result 1 if you want. A linear transformation of a multivariate normal random variable is also a multivariate normal random variables. Okay, now let's develop another result. Let's call it result 2. Okay, so yeah, so now everything is centered around multivariate normal and then also in the multivariate case. So your result 2 is saying the following. So again, you have a n-dimension multivariate normal random variables. And then here you have a transformation again, a linear transformation, AY. So AY is independent of another linear transformation for the same random variable y. So let's call it by. If the matrix A multiplied by the covariance matrix sigma multiplied by B transpose is equal to 0. So just to repeat this theorem is that, or this result is that for a multivariate normal random variables, this linear transformation AY is independent of another linear transformation BY, if and only if, or if you want, yeah. So right now I'm just going to write that if A sigma B transpose is equal to 0. Okay. So just to make it more general, you can let this A be a m by n matrix, and your y is a n by 1 column vector. And then your B, you can write it like, let's say K, okay, K by n, and then n by 1. So you have a n by 1 vector is independent to another K by 1 vector if this will give you 0. So let's check the dimension here. So A is m by n, your covariance matrix is n by n, and then your B transpose is n by k. So that means your 0 here is a m by k matrix of zeros. So you will have lots of zeros, and then there are m row of them and then k column of them. Yeah. But if your A and B are vectors, let's say one of them are 1, and that will reduce to a scalar 0 or a vector zeros. But in our case, we have a m by k matrix of zeros. Yeah. So this 0 is a matrix, not just a scalar 0. Okay. Just want to point out that. Okay. So this is another result. And now, or for the, I think we can finish in the next 30 minutes. Next is just to prove why this is the case. Okay, so we are going to prove this again using the momentary function that we have been focusing on. In particular is this one, the momentary function for A, y, and then by. So you will get a T1 and T2. And this is the if. So we want to check whether this equation holds. So AY T1 multiplied by the momentary function of by T2. So we want to check whether this is true or not. So if the left-hand side equal to the right-hand side, you can claim that this is independent. If they're not equal, then, well, this result is wrong. Yeah. So this is also similar to the homework problem here. Yeah, so if they are equal, you can claim that x1 and x3 are independent. If they're not equal, then x1 and x3 are not equal, not independent. Yeah, so we're doing the same thing here, except that we're doing for a linear transformation of a multivariate normal random variable. Okay, so I think from the previous result, we already know the moment function for a linear transformation for ay. So let me borrow the result from here. So that means we don't have any we don't have c anymore. So that means I'm going to borrow this expression here. So that means the moment function for ay is the exponential of, let me copy here. So T1 transpose A mu plus 1/2 T1 transpose A sigma A, there's another transpose here, T1. Okay, so here I'm just borrowing the result that we derived from the previous result 1 here. I'm just borrowing that, and then only the c is equal to 0, or there's no c anymore. So I'm borrowing, so let me write it here. So this is your result 1. I'm borrowing the result here. Similarly, the moment function for by, T2, is also the exponential of T2 transpose B mu plus 1/2 T2 transpose B sigma B transpose T2. So again, this is just result 2. I'm just borrowing it and then using our notation for ay and by, and then T1 and T2. Okay. So that means we have this part ready. We also have this part ready. All we need to get is this part, the left-hand side. We need to get the moment function for this joint, ay and by. Okay. So we want the following: the moment function for ay, by, T1 and T2. So we are going to use the definition, which is the expected value exponential of T1 transpose multiplied by ay plus T2 transpose multiplied by by. Closing that. So this here, let me write. It's just a definition that we provided here. Or, yes, for the multivariate case. So I'm just using this definition here. Okay. So next, we are just going to expanding this, and then we will get our strategy will be like this. So we are going to expand this expression here, and that will serve as our left-hand side. And then we need to multiply by the two terms on the right-hand side. And then let's verify if they're equal or not. And if they're equal, then we have proved the result 2. So that will be our strategy here. But as a second step, we need to simplify this expression. Okay. So let's see how we can simplify that, which turned out to be a little bit complicated. So we need to be a little bit careful when we work on this term here. Okay, so again, you have the integral, and then for this for this exponential T1, let me see. Okay, because this part is a little bit complicated, so I will develop it a little bit slowly. So you have the same thing, T1 transpose AY plus T2 transpose BY. Okay, so that is that, and then you need to multiply by the density function for your multivariate normal random variables. So that means you have the following. So 2 pi multiplied by negative n over 2, and then a determinant for a sigma covariance matrix 1/2, and then the exponential negative 1/2 y minus mu transpose sigma inverse y minus mu. Okay, and then dy. So here this y again is a n by 1 column vector. So it's a random vector, not a scalar anymore. So we are not working with scalar anymore. So we're just, everything is in terms of vector matrix multiplication. Okay, and this is just the density function f of y that we provided at the beginning of this lecture. Yeah. And this again is just a definition, or this is a definition for expected for momentum function, and this is just a definition for this expectation. Okay, so now we need to simplify it a little bit. And my next step is that I'm going to group this exponential term with this exponential term. So the product of exponential, again, is the exponential of sum. So we have the following. So the 2 pi negative n over 2, the determinant of a matrix negative 1/2. And then we have the exponential of, and then I'm going to write it in this way. So y transpose multiplied by b, and then minus 1/2 y minus mu transpose sigma inverse y minus mu. And then, just in case, let me use a square bracket for that. So I have grouped this exponential term with this exponential term, and then dy. But I haven't talked about the b here. So I'm going to define this new element b. Maybe not using two. Okay, so I'm just going to write b. Let me define it as a transpose T1 plus b transpose T2. So if you plug in b here, and then when you evaluate this, you will end up with this part here, except by just taking a transpose. Yeah. So, but I define my new elements b in this way. Okay. So next, let's examine another term. So here, let me write exam the following term, which I'm going to call it y minus sigma multiplied by b plus mu. So this is something that I'm, right now I'm just constructing something. Sigma inverse y minus sigma multiplied by b plus mu. Okay, so this is just something I made up here, and then I want to examine this new term that I construct here. By examining, I want to expanding this term here. And let's see what this term will give us in the end. But this is just something that by construction for now. But later you will see why I constructed this term particularly in this way. Okay, but right now this is just something I construct, and then let's examine this term here. So I'm going to rewrite it as y minus mu. And then minus the sigma multiplied by b. So we have this y minus this mu, and then I group them together, and then you minus the sigma multiplied by b. There's a transpose, and then y minus mu minus sigma multiplied by b. Okay. Next, I'm going to distribute these elements inside the square bracket. So you have like a AB multiplied by C multiplied by A minus B, something that look like this. So I want to use A multiplied by C multiplied by A, and then A multiplied by C multiplied by B, and then B multiplied by C multiplied by A, and then, yeah. And then you should get the following. Y minus mu transpose sigma inverse, and then y minus mu. Okay, so that is your A multiplied by C multiplied by A. And then let's get the B multiplied by C multiplied by B. Okay, so that means you have a plus, and then B transpose sigma inverse, and then B. And then we also have a 2 copies of A multiplied by C multiplied by B. So here we have the sign of minus, and then 2 copy of that. Y minus mu multiplied by C, where C is just the sigma inverse, and then multiplied by B, and then the B in our case is the sigma multiplied by B. Okay, then we have the, just let me simplify a little bit. Y minus mu transpose sigma inverse y minus b. And then you have this this term here, and then the sigma inverse, and then multiply by sigma. This will give you an identity, so that will cancel out. That means, and then you have 2 copy of y minus mu multiplied by b. I think there's a transpose here. Yeah. And then you have the B transpose sigma inverse multiplied by B. Okay. So now you should see why I have okay, let me further decompose a little bit to get our final result. Let me okay, so maybe let me write it here. So y minus mu transpose sigma inverse y minus mu. And then you have 2 y transpose b, and then plus 2 mu transpose b. and then plus a B transpose sigma inverse B. Okay, so now the question is, why do we want to construct this term in the beginning? So the reason is that we want to mimic whatever is inside the square bracket here for our joint homogeneous function. So you can see that it involving a y transpose B and then this quadratic form. So in the terms that I constructed here, we also have a y transpose B and then a quadratic form, except that we have two more new terms that we introduce by our construction here. So that means we can rewrite whatever inside the square bracket as the term that I constructed here, and then removing the terms, the two additional terms from here. Does that make sense? So let me continue from here. Okay, so what I'm going to do is that this is our result for the joint homogeneous function. And I'm going to replace whatever inside the square bracket by the term that I construct, and then removing the two additional terms that is not originally there. Okay, so that means we have the following. So the homogeneous function for AY, BY, T1, T2, that is equal to the integral of 2 pi n over 2 determinant of the sigma matrix inverse or 1/2. This part still stay the same, exponential. So now I'm going to bring this part that I constructed to here. Okay, so this is the terms that I constructed. And let me also put a negative 1/2 here. So that means we have reconstruct these two terms here. But by this reconstruction, introduce two more new terms that we don't want, or that is not originally in our formulation. So we want to remove it. So that means we want to further remove the two terms that we introduce. So we have to, because there's a minus sign here, so we have to add it back. So mu transpose B and then B transpose sigma inverse B. So these are the two terms that is addition, that is added, that's not originally there. But if we write it in this form, that means we have introduced these two new terms, so that we need to remove them again. So that will be the logic here. Okay, and then dy. And now the question is, why do we want to make that change? The reason is that we can bring this term, because it does not involving the random variable y. So we can move this thing outside the integral here. So we will have the mu transpose B, and then plus I think there's a 1/2 here because I multiply 1/2 here, and then this is 2. There's no 1/2, so there's a 1/2 here. Okay, so 1/2 B transpose sigma inverse B. Okay, so this is the part from here that does not involving random variables. So I can move it outside the integral. And then the remaining parts stay inside the integral. And then we have the following. So here are the normalizing constant. And this will serve as our new exponential term. B plus mu, closing that, transpose sigma inverse y minus sigma multiplied by B plus mu. So now, after all these construction and substituting all the terms, what we essentially have done is that inside the integral, this is a density function for a multivariate normal distribution. So what we have construct from all this long derivation or this construction is that inside the integral, we have the y following a normal with the mean sigma multiplied by B plus mu, and then sigma matrix. So that means everything here is a density function for a normal random variables. So that means this entire integral should be evaluated to, or what does this equal to? So this whole thing should be equal to 1, right? We integral over the density function with respect to the vector dy. So by construction here, we have the E multiplied by mu B plus 1/2. Multiplied by B. Okay, and then multiply by a 1 here. So the reason for all these construction, all these things, and then the grouping, adding back 2 more terms and removing 2 more terms, we essentially construct a new density function for a new random variable. This integral to 1, and then we have this final form as our moment generating function for this joint ax, ay, and by. And then let's substitute back for B. And this B, again, is A transpose T1 plus B transpose T2. And then your final expression should be exponential mu transpose so I'm going to distribute the 2 terms here plus mu transpose B transpose T2 plus 1/2 A transpose T1 sigma multiplied by A transpose T1. And then you also have the B transpose T2 sigma inverse, and then B transpose T2. And then you also have the cross product term. So A transpose okay, so there should be another transpose here. Okay, so this is your final expression after you plug in the b. And this is your homogeneous function for ay, by, t1, and t2. Okay, so like I said, this part is a little bit complicated because you need to do it by construction to show that the homogeneous function for a joint of a two linear transformation random variables into this form. And now we need to check the right hand side. Is this equal to ay t1 multiplied by by t2? So we have homogeneous function for ay look like this. Homogeneous function for by look like this. So there are two terms and then another two terms. But here we have 5 terms. And then, so right now they are not equal, but they are equal with the condition from here. A sigma B transpose equal to 0. This term will go to 0, and then you will have this one and this one from your homogeneous function of ay, and then this part and this part from your homogeneous function for by. And then when you take the products, you will have the sum of these 4 terms, and then they will be equal to the joint homogeneous function for ay and by. So basically this is proving that if you have two linear transformation ay and by, they are only independent if A multiplied by sigma multiplied by B transpose equal to 0. Yeah. So if they are equal to 0, this term will go to 0. You're only left with these 4 terms, and that is the product of the right hand side. And then they are independent. AY and BY are independent. Okay, so this is just a proof for the result 2. And later, we were going to use the result 2 to prove something else. And that something else will be very useful for, let's say, hypothesis testing or confidence interval. But everything from there is all based on this result 1 or this result 2. And the result 2 is based on result 1. Okay, so I think I can stop here and yeah. And let me know if you have any question.